Hello guys, how are you? This is Jaime, your teacher at home. As probably you are still remain at home, we are forced to be here. Today I'm going to upload this video. We are going to continue with the classes as you have received some emails. Things have been changed. We have to be at home. We have to continue with the lessons, so I will give you some pieces of videos with contents, as well as some other documentation from the web, from the book that is recommended into the bibliography. So today we start with the IPv6 protocol. We saw in the previous classes the version 4 of this protocol. We studied the datagram format, the fragmentation, where one packet arrives to a network that has a smaller MTU, so we have to fragment. IPv4 addressing, class full, classless, the notation, the net mask, the subnetting concept, and finally the NAT functionality to translate private API addresses into public ones. So today we are going to learn the IPv6 protocol. So the initial motivation is that we were running out the number of IPv4 public addresses. So the specific motivation was in the mid-90s to define a new protocol to enlarge the length of the IPv4 address field. So the idea was to try to avoid this expiration. 32 bits for addresses were too small, so we needed to have a bigger field. So if you remember when we were discussing or drawing the IPv4 packet, we have an IPv4 header, IPv4, sorry for drawing it, is the first time I use this tool, IPv4 header and data or payload, right? We had a minimum length of the IPv4 header of 20 bytes. Then we can have optional fields, and after that the data. Okay, so the difference with the IPv6 datagram is that we have also an IP header, IPv6 header. We have the data, but we don't have a specific field called options. So we don't have options. The length for the IPv6 header is 40 bytes. It is fixed. And another functionality is that no fragmentation is allowed. So we cannot fragment on a router. We can only fragment on a source host. In the case of IPv4, we could fragment on routers once one packet arrives to a router that is connected to a network with a smaller MTU, so we are allowed to fragment and reassemble a destination. Here at IPv6, we don't have this possibility. The router will announce with a specific packet that I will mention later that this packet is too big for the next network, so the source host could create a smaller packet or just decide to discard the operation. So this is the main difference. We have a bigger header, fixed header, no options, and we will see many other differences in the next slides. This is the format. Of the header, we have 40 bytes header of a fixed header length. Next, I'm going to explain all the fields as usual. So the first field is called version. In this case, we will have number 6 instead of in the case of IPv4 we have the number 4. Then the next field is called priority. Is more or less the same functionality as the type of service field in the IPv4 header, trying to give more priority to some of the flows in the traffic through the network. So a very important concept is the concept of flow. A flow is a sequence of packets that are related, that are sent from a source to a particular destination. So we can give a specific priority for different types of flows. All these flows will have a label or identifier that relates all the packets belonging to the same flow. For example, if you remember the case of fragmentation, the identification field, all the fragments belonging to the same IP packet had the same ID field in order to reassemble, to know which of them are related and reassemble them at the destination. So in this case, the flow label refers to all the packets belonging to the same flow. Next field, payload length. The payload length refers to the length of the payload. So we have the IPv6, in this case, header, and the data is the payload. This is the payload length. So now I'm asking you, why is it necessary to have the payload length? Is it necessary to have the length for the whole datagram? Yes, no, and why? The next field is next header. This next header field is the same as the protocol field we had in IPv4. So it refers to the type of PDU we will find in the next layer. For example, a TCP segment, a UDP segment. So a specific case in this next header is options. So we can have a datagram like this, IPv6 datagram, with the header, IPv6 header, and then we can have a next header for the options. So this options field doesn't belong to the header but can be appended to the header in the middle between the original unfixed header and the payload. Okay, this is the data. This is the option header, not option field. So at the end we have options, but we don't have a field for options. It's a next header. Well, and finally we have the most important fields that are source and destination IPv6 addresses of length 128 bits. With this length, we have a very big range of IPv6 addresses, and it is expected that no device in the world will be forced to use a trick like the NAT or private addresses, because each device could have any IPv6 and public address. So finally, we will have the data. As I told you, the data is the next PDU from the transport layer. Other changes from IPv4 to IPv6 in the sense of having the format. First of all, the checksum is removed. So if you remember, we have the checksum at layer 2, layer 3, and layer 4 on the IPv4 stack, let's say. So while they were trying to migrate from IPv4 to IPv6, they said, why if we don't reduce the complexity of the protocol? If we have the checksum at layer 2 and layer 4, and the checksum must be done on each hop, on each router, if we remove the checksum at IP, so we are speeding up the process. So they decided to remove the checksum at layer 3 in IPv6. So the option fields, as I mentioned in the previous slide, it's allowed but outside of the header. There is a specific header undefined by the next header field. Okay, you have options but outside the header. And finally, there are some other protocols like ICMP. ICMP stands for Internet Control Message Protocol, that is used for error checking or error notifications in the network. For example, if one packet is finally arrives to a router, this packet arrives to the router and the TTL is set to 0, the router will discard the packet and will send back to the source host a message of type ICMP saying, okay, your packet has died, you are notified that you can do what you want. If you want, you can send a packet again or stop it. So in the case of ICMP v6, we have these types of packets. For example, for the fragmentation. So fragmentation is not allowed on IPv6. If the host sends a packet to a network with an MTU that is smaller, this packet arrives to the router, and the router is not allowed to do fragmentation because of IPv6. So the router can create an ICMP v6 packet of type packet too big to the host that send the package. So it can decide to reduce the size of the packet and continue. Well, once we know the fields for the IPv6 header, the datagram format, we can think on, well, the systems implement IPv6. Some of them are still implementing IPv4, which is the hybrid functionality. So this term is called transition from IPv4 to IPv6. So we can think, okay, or to say, at day D, time T, all the routers, all the systems in the world must be improved to IPv6. But as you can imagine, this solution is not feasible for enterprises with hundreds of routers or ISPs with thousands of routers. So the transition is incremental. We have to decide which is the specific subset of routers to be firstly improved and then continue in the next years with another stage of improvement. So it's not straightforward. So there are no flag days, not a day that we can say everything will be working using IPv6. So during this transition, which is the operation at the network with hybrid IPv4 and IPv6. So this concept is called tunneling. So the idea is to make a trick, and if we have an IPv4 datagram, like in the one in the slides, we have the IPv4 header, IPv4 header, and then on the payload we will have the full IPv6 datagram. So in this way, if we want to send an IPv6 datagram from a source to a destination, and we find an IPv4 network in the middle, we can bypass this IPv4 network. We will see it better in the next example. So this is the final situation. In this example, we have a network with a physical view like this one. This is our network or our path to be followed. So we want to send something from A to F, right? So we want to send an IPv6 datagram from A to F. So we want to create the IPv6 datagram with the source A, with the destination F, okay, and with the data, perfect. Then once we traverse router B, we have to move to an IPv4 network. In this case, it is called IPv4 tunnel in our logical view. So this IPv6 datagram is encapsulated into the payload of an IPv4 datagram. So this IPv6 datagram is included here. And as well, on the IPv4 datagram, we have the header. During this network, IPv4 network, so all the packets are IPv4. And on the payload, we will have the corresponding IPv6 and the header. Okay. So finally, we exit the tunnel. Imagine we are driving a car and we face a mountain. We have to go through a tunnel. So this is the same. At the beginning, we have to turn the lights on. Then, when we exit the tunnel, we should turn the lights off. So in this case, we extract the payload and we will have the original IPv6 data with the source A, with the destination B, the same as we created here. Okay, this is the concept of tunneling. The principle of sending an IPv6 packet from IPv6 router to another IPv6 destination router by means of a IPv4 tunnel. So this is the solution of the previous example. And finally, the adoption. So we have some examples on Google. The 80% of clients have access to services via IPv6. In the US government, we have 1/3 of all the systems that are IPv6 capable. But as you may know, it's very complex to modify a protocol that is the core of the internet. The IP protocol is the core, the glue of the internet, of the TCP/IP stack, so it's very difficult. It's like build a new house. So if you only change the application protocol, it's like, okay, you can paint the walls, maybe using another color. The neighborhood will look at you very surprised. Maybe they want to use the same color as you, but if you want to change the whole house, it's more complex. So you have to think on the application level changes in the last 20 years. For example, the World Wide Web or Facebook, streaming media or Skype. It's difficult. What else? I think that's all. This is the first piece of video I will upload to the campus virtual room, and I will be back with some other content. Bye bye. Have a nice day.